Welcome to this PAG 3.1, Investigations to determine the resistivity of a metal wire. This PAG requires us to create this circuit. And so I've made it here. Let me talk you through, help you to see how this is the same as what is on the paper here. So I've got a variable power supply that goes up to 12 volts. That's just here. It has an internal switch, so I don't need to put a switch into my circuit. The wire comes out here, first of all, into an ammeter, just there. Turn it on. And I've got the ammeter actually plugged into the 10 amp section here because it's quite a reasonable current that will flow through this. Now I've chosen to use a multimeter here because it's just more sensitive than these ones here. These are limited, their range is fixed, whereas here I can select the sensitivity so that the range is as good as it can be. And from the ammeter, we have the wire coming down into this wire, whose resistivity we're trying to measure. Connected to this wire is a flying wire, just here, that attaches at any length that we like. And we can measure the length because the wire is mounted on a meter stick. And this wire goes to a voltmeter that spans and finds the voltage across this wire by connecting from the flying wire back to the ammeter. And then finally, from the top of this, we connect to the sliding scale of a rheostat. The rheostat itself is plugged in across here and here. All this rheostat enables us to do is select the amount of EMF being supplied to this here. So by changing this slider on the top of the rheostat, we can supply the circuit with whatever voltage we like to affect the current remaining the same. Now in this, in the formula for resistivity, think of the variables that are in it. The area of the wire, the resistance of the wire, and the length of the wire. Now the resistance of the wire, if the temperature is kept constant, is the voltage divided by the current. And so what you can see, I can measure the voltage. If I keep current the same and area the same, then I only have two things in this whole thing. I have the length of the wire and the voltage. And with that, I can calculate the resistance. So what I'm going to need to do is I'm going to need to place my flying wire at some distance, like 10 centimeters, attach it here. I'm going to need to adjust this to get a particular current on there. And say I wanted 1 amp going through this wire. It would always need to be 1 amp. So I would adjust the rheostat until it's 1 amp, and then I would record the voltage. Then I would move the wire to 20 centimeters, for example, move the rheostat until it's back on 1 amp again, and then record the voltage. And then again, I would move the wire until it was 30 centimeters, move the rheostat until it's on 1 amp again, and measure the voltage. That way I'm keeping the current the same, I am changing the length, and I'm measuring the voltage. We want to take a good amount of data here, so I would actually suggest, first of all, picking a value of input voltage that gives you the full range. We've actually found a higher voltage here would give you the full range of the meter. And the second thing is you want lots of data, every 5 centimeters or so, just to see. So we're going to do that now. We're going to go take the data and record for a set of different measurements. Now one thing that is important is that this wire will get quite hot. To limit the effect of the heat, there's multiple things you could do. You could put the whole thing in a distilled water bath, or alternatively, switch it on, take the reading, switch it off, to give it time to cool down between each measurement, so you don't have the cumulative effect of heating over many, many minutes when you're taking your later results. Let's take some measurements. As you have more and more wire here, it's going to provide more and more resistance against the flow of electricity. And so we're going to find that this wire will start to get hot as you go down here. It's going to ruin your results. So here's a trick. What I would do is I would turn it on, adjust the rheostat till it gets to the current that you want to see, switch it off. Allow it 30 seconds to a minute to cool down, and then switch it on quickly and take the results. 71. Another thing to consider is the consistency of where I'm attaching this crocodile clip. Some of these flying wires have like a screwdriver attachment for accurate placing. But with this we can do it. We just need to be consistent. I'm going to use the left-hand side to always represent and line up with the measurement just there. So you can see I'm going to get my head square over to avoid any parallax error. And now I can see that it's exactly lined up on the left-hand side. Now if I change the angle of this, you can see that it now looks like in a slightly different place. So I need to get my head directly above when measuring this. So I've now got all of the data that I need, apart from the calculations for the cross-sectional area. The very next thing we need to do is accurately determine the area. And for that, we're going to measure the diameter of the wire. Now you could use a micrometer or a vernier caliper. The key thing is you need a vernier caliper with one of these. This is a thing that basically when the pressure reaches the same amount, it will start to slip. So you can't accidentally crush the wire. The key thing is this, when we close it to the point where it starts to slip, we're going to zero it so that the 0 point is captured. Now with this, I think we should measure about 6 different diameters at different points in the wire, at slightly different orientations. And so from that, we're going to then process that to measure the area, which is important for our calculation. So take a look at this. Here is my diameter, and I've now divided it by 1,000 to get it in meters, and maintaining the number of significant figures. As we go across and we process this, we need to always make sure this is to 2 significant figures. So this is going to be, when we put into the formula for pi r squared, where r is d over 2, the diameter divided by 2, then we're going to get, is it 1.9 times 10 to the minus 7. And you notice this is to 2 significant figures like all of the previous. The 0 is not a significant figure. And we're going to make sure that we now fill it in all the rest, and we're going to work out the average at the end. So a note of caution, to keep the number of significant figures into this column here creates a rounding error, because 5.0 times 10 to the minus 4, when put into this formula here, gives 2.0 times 10 to the minus 7, but so does 5.1. Now these are different numbers, but it's rounded them to the same number, which means when we average this column, we get to 2.0 times 10 to the minus 7. If we average this column before the rounding error and then feed that answer into here, we actually get 1.95 times 10 to the minus 7. And now this, to 2 decimal places, does round to that, but this I think is ever so slightly more accurate. So I think we might use this one here and just extend it down to one more significant figure. So we're going to now use this as the area in meters squared in the following step. Resistivity can be given by the formula rho is equal to R A over L, where L is the length of the wire, A is the cross-sectional area, R is the resistance, and rho is the resistivity. For something that is an ohmic conductor, like a wire, then we can use Ohm's law, that the resistance is found by doing the voltage divided by the current. So the resistivity is going to be voltage divided by current multiplied by area over length. Now we're going to rearrange this into a form that's more handy to us. We're going to put the voltage over length is equal to rho, and it would be current over area. Like that, just a rearrangement of those things. Now that's really useful to us because current in this experiment was kept constant, and so was the area. I mean, it didn't get any wider, and so these two are just constants. This is what we're trying to find, and these two are the things we measured. The length was the independent variable, so we could draw that on the x-axis of the graph, that the length measured in meters against the voltage, the dependent variable, measured in volts. And now what we're going to do is we're going to plot our data, the voltage against the length, and see what relationship it has. Now the reason why I want to do this is we're hoping that if it is a linear relationship and forms a straight line, that you can see the gradient of that line, V divided by L, should equal the resistivity multiplied by some constants. So what we will have here is a known gradient is equal to an unknown quantity multiplied by some known constants, which means we should be able to find the unknown quantity. What is really important is I need to make sure that how I've recorded my data is scientific, that my table is correct, that not only is the precision down the column kept the same because the instrument recording this isn't getting more or less precise, it has to have the same number of decimal places as we go down. When I process numbers across, it's the same number of significant figures. Also, there's no units in here. The unit is in the header. It's the quantity divided by the unit that gives the pure number as recorded. It should be boxed in with a ruler. The graph you could draw on paper, or you could draw on a program like this. Within your PAGs, it's best to do some on paper and some using a computer. The computer, of course, can give you a mathematically modelled line of best fit, but sometimes it's worthwhile practicing drawing one by hand. So you can see I put the data into this graphical program. I've got the voltage on the y-axis and the length on the x-axis, because length was the independent variable and voltage was the dependent variable. Here is my data, and you can see it's fairly good. There's one or 2 points that are a little bit away from the line, but it's okay. When I look down the line, I can see that it's basically straight. That's a very important thing, is looking down your data. Is it a straight line or is it curved? Now in this particular instance, I'm going to go with the idea that Ohm's law was being obeyed, that we were keeping it at a reasonable same temperature, and so therefore I can plot a line of best fit. And so there it is. And so this means the gradient of my graph here is 2.79. And so that's a number that I'm now going to use in the rest of my calculation. If voltage divided by the length, this here is the gradient, then we can work out this, because the resistivity would be the voltage divided by the length, divided by the current divided by the area. All of these are known, so 2.79 divided by 1 divided by, and the area, which was 1.95 times 10 to the minus 7, which gives a resistivity of 5.44 times 10 to the minus 7 ohm meters. So what is the identity of our unknown wire? Well, closest one to this is the resistivity of Constantan, a type of wire used in this sort of thing, has a resistivity of 4.9 times 10 to the minus 7 ohm meters. So I would say almost certainly that's Constantan. The extension materials for this PAG are quite good actually, because they get us to practice looking at uncertainties. Now, one of the very first things it asks us to do is to state what the uncertainty is on the measurements that we took. Now, how we gauge this is we look at the precision of the apparatus. the voltmeter, the meter ruler, and the vernier calipers are the three measurements that we took. And we look at the smallest increment, and though, okay, for the voltmeter it was a digital scale, it could read down to 0.01. So it was sensitive to half of that value. So the actual sensitivity, or the uncertainty, on the voltmeter is 0.005 volts. The uncertainty in the length, given it was a meter ruler that measured to the nearest millimeter, is half a millimeter, 0.005 meters. And the uncertainty in the distance, or the diameter, was measured with the vernier caliper. Well, the vernier caliper was 0.01 millimeter, and so we've got 0.005 millimeters. Of course, divide that by 1,000 to work out its uncertainty in meters. Now, one of the things it wants us to do is to add error bars to our graph. And of course, these uncertainties are tiny compared to the uncontrolled things like the temperature and such like. So these are going to be really tiny on our graph, but we're going to draw them anyway. So I've now added those systematic uncertainties to this as error bars. You can see this is the code that I've used for Desmos. That basically I've made an error bar that's 0.005 each side of the data point. Now, in terms of the physical length, you can see that's the error bar this way. It has just about resolved the error bar. You can just about see it. It is slightly larger than the plotting point. That's because a millimetre, or half a millimetre, is actually significant compared to the size of a metre. So that is a measurement that would be slightly larger. Whereas the voltmeter, the actual vertical scale, it's so small that 0.005 of a volt on a scale where you're measuring in between 0 and 1 volt, that's so tiny that you can't actually see the vertical error bar. Now, what that means is, and given that you can see that there is some fluctuation that is bigger than these errors, it says to us that the systematic error was not the largest source of error. There must have been some random error caused by some uncontrolled variables, such as the temperature of the wire. Now, the next thing it's going to ask us to do is draw the best and worst line of best fit. Now, when we have got a line like this, where we've only put on the systematic error bars and not the random ones, what we're going to have to do is be quite subjectively draw two lines and think which two could both represent the very best and worst line. So let's have a look at that. So having drawn a line of best fit, and Desmos has used linear regression to draw and to calculate the very best line for this set of data, that's the red one right there. I noticed that it actually misses some of the data points, like this one over here and this one over here, and it misses this one over here. So it's possible for me to also draw a line of worst fit, like the worst fit that fits this data. And so what I've done is I've drawn a second line and I've altered the intercept and the gradient values so that this second line actually intercepts some of these points that are higher down at the bottom and lower down over there. Now, I think that is about the worst possible line that still goes through some of those data points. And so for that, I've got now two values for the gradient. I've got the value of the gradient of the line of the best fit, and I've got the value of the gradient for the line of worst fit. To work out an uncertainty on the gradient normally, what you must do is you must draw the steepest and shallowest possible lines of best fit. And that you know that the uncertainty in the gradient is going to be the gradient of the steepest minus the gradient of the shallowest divided by 2. So we look at how much steeper than the line of best fit the steepest one is, and how much shallower than the line of best fit the most shallow one is, and then we divide that by 2 to basically get that size uncertainty. Now we can find out what that difference is just by doing m steepest, the steepest gradient, minus m best, which is the line of best fit. So in most situations you draw two lines, a steepest and a shallowest. in this program, we've actually automatically got it to calculate what is the best line of best fit. And so what we can also do is we can obtain the same thing by doing the steepest minus the best. Now in this case we don't have to divide by 2 because we've not gone above and below. The value of the steepest gradient and the value of the shallowest gradient divided by 2 is giving you just the difference between the value of the worst line of best fit and the line of best fit. Here we don't have to divide it by 2 because we're just talking about that difference anyway. So we can use this here. And so basically the uncertainty in the gradient is going to be 2.794 minus 2.700. So the uncertainty is going to be 0.094. That's the uncertainty. So my actual value of gradient here is going to be equal to, what was the absolute value? Well, the absolute value was 2.794 plus or minus 0.094. That's the uncertainty in the gradient, the volume per unit length. And so the units here, voltage divided by length, so it's volts per meter. That would be what the gradient represents. How do we work out the uncertainty on the thickness measurement? Well, there's a slight issue there because we took multiple measurements and they're all slightly different. Now, a really primitive way of doing it is by looking at the range. If we look at these values here, they go from 4.5 times 10 to the minus 4 up to 5.3 times 10 to the minus 4. That's a range of 0.8 times 10 to the minus 4. Primitively, we can say that half of the range is equal to the uncertainty, so 0.4 times 10 to the minus 4. Now, that is a primitive way of doing it, because the actual correct way of doing it is to also incorporate the systematic uncertainty that's come about due to the precision of the vernier caliper. That was accurate, as we found, to 0.005 millimeters. So the true uncertainty is going to be equal to the square root of that uncertainty squared plus the standard deviation in these repeats squared. So let's process that and see the size of this error. So here the uncertainty in the diameter is equal to the square root of the systematic uncertainty due to the precision of the caliper plus the standard deviation due to the ranging data that we got when we did multiple times all squared. The answer actually comes out as about 0.271. I mean, that really doesn't change the value, not to that number of significant figures. Now that's very interesting because when we said that it was half of the range would have been 0.4. This is about 0.3. So the actual uncertainty is slightly smaller, times 10 to the minus 4. And the actual uncertainty is slightly smaller when you calculate it like this than it is if you take half of the range. But because they're similar values and they scale similarly, they're quite often one is considered like the other one. But notice again that the uncertainty that comes from the precision of the apparatus is not the driving uncertainty. This variability from one repeat to the next is simply because this wire isn't the same thickness. It's getting thicker and thinner. Like the accuracy with which it was made has meant that some areas are just naturally thicker and thinner than other areas, and that variability was greater than the sensitivity of the calipers that were measuring it. And so the uncertainty is dominated by the fact that the thickness of the wire is not particularly constant. Now the next thing we need to do is we need to process this uncertainty to work out what the uncertainty in the cross-sectional area is. So how does this relate to the uncertainty of the area? Well, the uncertainty in the area relative to the area is going to be equal to 2 times the uncertainty in the diameter divided by the diameter. And that is simply because the equation that links them is pi r squared. So we've got the error on the distance measurement twice, and that's why we've got 2 of them just there. So what we need to do is we need to put this equal to 2 times 0.271, the uncertainty in the value, 271, divided by what the actual average was. What was the actual average? 4.983. 4.983. This is going to tell us what the size of the error, or the relative error, is going to be. This gives us a value of 0.1087. So this uncertainty is equal to 0.1087. Check I've got that right. Yeah. So I know that the error of A relative to the value of A is 0.1087. My average area, I got it as 1.95 times 10 to the minus 7, which in millimeters squared is, I think, 19.53 millimeters squared. That's the value of A. So if I've got this divided by this is equal to this, and this times that will give us the uncertainty on the error measurement. 19.53 times 0.1087. It's about equal to 2 point something millimeters. Let me just go and check. So the uncertainty on the area is 2.12 millimeters squared. Now, of course, we've done our area meters squared, so we're now going to have to do a conversion of 2.12 millimeters squared into meters squared. I've run out of board, but if we remember that the conversion between millimeters squared, if we take our millimeters squared, we square root it, we divide it by 1,000, and then we square it again. This will tell us what that is in meters squared. So it'll be 2.12, I think, times 10 to the minus, times 10 to the minus 8, I think. I'm gonna get a calculator and work that out. So I think 2.12 times 10 to the minus 8 meters squared. Let's go see if that's right. So in trying to calculate the uncertainty of the resistivity that we've calculated, we've actually got the uncertainties of these various different parts of the things that have gone into calculating it. V over L was the gradient of the graph. The uncertainty in the gradient of the graph we found just here. So it was equal to 0.094. The uncertainty in the area, well, we just found that out just there. So we have that. We also have the uncertainty in the current, even though the current was fixed. We still only knew it to the precision of the apparatus of 0.005 amps. So how do we work out, for something as complicated as this, well, what we need is that we know that the error of the resistivity compared to the resistivity squared is going to be equal to the error of the other three things. They're straightforward multiplications or divisions, so the relative size of their errors relative to their actual values. So the error in the gradient, the voltage divided by the length, compared to the value of the gradient, the voltage divided by the length, squared, plus the error of, in this case, the area compared to the area itself, squared, plus finally the area in the current compared to the value of current itself. So now we need to substitute these values in. I clearly need some more space on my blackboard. I'm going to clear some space over there, and then you'll see this calculation go through. So there we have it. There's the relative uncertainty in the resistivity compared to the value of the resistivity squared is equal to the all of those values there. We've got the uncertainty in the measurement divided by the actual measurement itself squared. Put them all together, we find the relative uncertainty is 0.1168. So we now need to find the absolute uncertainty. And so we take the value of 5.44 times 10 to the minus 7 and times it by the relative uncertainty, and we end up with an answer of, was it 0.68? I think, no, 0.63 I would suggest. Yeah, 0.63 0.63 times 10 to the minus 7, which means that our resistivity is equal to 5.44 times 10 to the minus 7 plus or minus what would be 6.3 times 10 to the minus 8, or another way we could write that is 5.4 plus or minus 0.63 in brackets times 10 to the minus 7 ohm meters. And that's how we process PAG 3.1. Wait, there's one more thing it asks you to do, and that was to work out the percentage difference between the value we've calculated and the actual value of the resistivity of constantin. So let's have a go. So how do we work out percentage difference? Percentage difference is going to be basically the measured, that's what we got, minus the reference, which is the actual value of the resistivity of constantin, divided by the reference, the actual value of constantin, times 100%. And so we got 5.4. The actual value is, what is the actual value? It's 4.9 divided by 4.9 times 100%. That gives us approximately about 11% difference. And that's the very final step. No, it's not done, because there is actually one more thing, which is where did we get the actual value of the resistivity of constantin? Well, we found it online, and one of the things that we can do here to gain perhaps the ticking off of an extra standard is correctly reference where we got the information. So this is the information in what's called an APA style of referencing. There are other styles, Harvard for example, but this will do. And so basically what we've got here is the title of the document that was found online, the date at which it was retrieved, and then the full URL of that website. So if I clicked on that, it would take me straight to where I found that piece of data. If I include this next to my research value of the resistivity, then I would definitely be ticking off the standard for correctly citing my sources.